Hello dear friends, a great welcome to this series on engineering mechanics. Myself Jairaj MP. This is class 6 of the series and the contents include moment of a force about a point in the scalar format and also an example problem for the computation of moment of a force about a point in the scalar format. So let us start our class. So to explain the concept of moment of a force about a point, we consider a simple practical case. For example, referring figure A, we can say that here a wrench is used to unscrew the bolt that is located at the point O. So here as you can see that a force F is applied at the end of the handle. Okay, and obviously as we can see the effect of the F is to produce a turning effect at the point O where the bolt is situated, and it tries to unscrew the bolt because it creates a moment in what we call as a turning effect in the anti-clockwise direction. Okay, so this turning effect which a moment produces about a point is what we call as the moment of a force about a point. So how do we calculate the moment of a force about a point? So look here. Here we know that the turning effect that is produced at the bolt location, that is at the point O, by the force F can be written as MO, that is the moment of the force F about the point O is equal to F into D, where F is the magnitude of the applied force and D is the perpendicular distance that is measured from the point O, okay, onto the line of action of the force F. So it is very important that D has to be measured perpendicular to the line of action of the force F. Now from this sketch, it is very easy for us to say that if we apply the larger force, it applies a larger turning effect about the bolt location O. Again, if the distance D is larger or with increase in D, the turning effect produced at the point O will also be larger. And accordingly, we know that the moment of a force F about a point O is equal to F into D. So the method of increasing the turning effect at the point O is either increase F or increase D or increase both. Okay, so we conclude that the moment of a force about a point is equal to the product of the magnitude of the force F and the perpendicular distance D measured from the point O onto the line of action of the force F. And this perpendicular distance D is also known as the moment arm. Now here is shown another case. Look here, in case A, what is done is that the force F is applied perpendicular to the handle of the wrench. In case B, on the other hand, as we can see, that this force F, it is applied at an angle theta to the handle of the wrench. So in this case, obviously we know that the perpendicular distance that is measured from the point O onto the line of action of the force F, it will be D into sine theta. It is not D, which means that in this case, where the force is applied at an angle theta, the value of the moment arm, it reduces from D to D sine theta. So it does mean that the best way to produce the maximum turning effect is to apply the force F normal to the handle of the wrench. For any other angles, we know that the corresponding turning effect will be less. So what we can say that D dash, the moment D dash in case B is equal to D into sine theta. Okay. So please remember that the moment vector, that is vector MO about the point O, is a vector quantity. The moment about a point is a vector quantity. Its definition is complete with the specification of its magnitude as well as the direction. Okay. Now remember that the unit of the moment, magnitude of moment about a point will be obviously either Newton meter or LB feet, whether we are following the SI system or the LBS system. Now, we have defined the magnitude of the moment as F into D. Now, what about the direction? In order to demonstrate how to clearly define the direction of moment vector, here is a sketch. As you can see that here the force F is applied at a perpendicular distance D from the point O. Now, magnitude is known to us, m is equal to F into D. Now, how we can define the direction of the moment vector? So here we have to follow some guidelines. Number one, the moment vector, it must pass through the point O about which the moment is calculated. That is criteria 1. And criteria 2 is that the moment vector MO, it has to be perpendicular to the plane containing the force F and the momentum D. So here you can see that the moment vector, it makes an angle 90 degree with the plane containing F and D. Please remember that the plane containing F and D is marked in light gray shades color. Okay, and so we know that it is normal to the plane containing F and D. Now, whether it is directed away from this plane or it is directed towards the plane, it's very simple. This can be determined by means of the right hand rule. So obviously, as we can see, this force F, it produces a counterclockwise moment about the point O. So in order to decide whether this vector MO is directed away from this plane or towards the plane, we just fold the fingers of our right hand in the anti-clockwise direction to find that the thumb is pointed upward. So which means that the moment vector MO in this case, it is directed upwards, that is away from the plane containing F and O. So this is how we decide the direction of the moment vector. Remember once again that the moment of a force about a point is a vector quantity. So we need to specify perfectly the magnitude as well as the direction of the moment vector. Now in some cases, what happens is that our rigid body may be subjected to a system of forces. For example, as shown here, I have shown a set of forces F1, F2 and F3, right? And all these forces F1, F2, F3 are essentially in the XY plane, and the perpendicular distance that is measured from the point O onto the line of action of the various forces are identified as D1, D2 and D3. Now it is important in the calculation of moments that we assume some directions as positive. For example, let us assume in this case that all the counterclockwise moments are positive. So obviously looking to this sketch, we can say that F1 produces a counterclockwise moment of F1 into D1 about the point O. On the other hand, F2, it produces a clockwise moment as marked here, M2 is equal to F2 into D2 about the point O. And regarding the force F3, it produces a counterclockwise moment of M3, that is equal to F3 into D3, which means that the total moment of or the turning effect, the total turning effect produced by all the forces F1, F2 and F3 at the point O can be written as MRO, that's the resultant moment of all the forces about the point O is equal to F1 D1 minus F2 D2. Remember, while F1 D1 and F3 D3 are anti-clockwise or counterclockwise, F2 D2 is clockwise, so we have assigned a negative sign. Now suppose that MRO happens to be positive. It does mean that the net effect of MRO will be again counterclockwise. On the other hand, if MRO works out to be clockwise, it does mean that happens to be negative. It means that it will be a net clockwise moment acting at the point O. So this is all regarding the concept of moment of a force about a point, how to obtain its magnitude. So we know that the moment of a force about a point O is MO is equal to F into D, where F is the magnitude of the force and D is the momentum which is measured from the point O perpendicular to the line of action of the force F. And we also know that the moment of a force about a point is a vector quantity whose direction has to be decided based on the criteria already discussed. So now let me take you to a very simple example number 1, wherein I have given you a set of simple structures which are essentially two-dimensional structures, and I have asked you to calculate the moment of all the forces in each case about the point O. So Please remember that the moment of a force about a point can be obtained either in the scalar format or in the vector format. Normally, we go for the scalar format for the convenience only for the 2D structures, where the moment calculation involves a 3D space. Obviously, the best and the simple method is to go for the vectorial format, which will be discussed in the next class. So let us go to the various structures here. In case A, which is shown here, it's a simple rod, which is subjected to a perpendicular force of 100 Newton. So obviously, in this case, we know that the moment of the force 100 Newton, that is at the point O, MO is equal to 100 into 2, that is 200 Newton meter. Now here is shown a simple bent L-shaped structure wherein at the tip is applied a 50 Newton. So what will be the moment of this applied force of 50 Newton about the point O? It is nothing but the magnitude of the force, that is 50, into the momentum. That is, you have to measure from the point O, the distance D has to be measured from the point O normal to 50 Newton, that is 0.75 meters. That is 37.5 Newton meter. In the scalar format, please mark the moments as clockwise or anti-clockwise. So here I have marked it as, obviously this will produce a clockwise moment, and I have marked it in the blue color. Now going to the third simple structure, as you can see that the first part is straight and the other part is inclined 30 degrees to the horizontal, and the end of this bent structure is subjected to a 40 pounds force downward. So in this case, we can readily obtain the moment of the applied force about the point O as 40, that's the magnitude of the force, into the distance. Please remember that the momentum should always be measured perpendicular to the line of action of the force F. So in this case, it is 4 plus this distance, that is nothing but 2 cos 30. So this works out to be 37.5, and we know that this definitely produces a clockwise turning effect at the point O. So we define the magnitude as well as the direction for the moment calculated at the point O. Now here is again a simple 2D structure, okay, and the geometry of the structure is already given to you. The straight part is of 3 feet in length, and the inclined part is of 1 foot long, and is inclined at 45 degrees. In this case again, let us compute the magnitude as well as the direction of the moment at the point O. So MO in this case is magnitude of the force, that is 60, into what's the perpendicular distance measured from the point O onto the line of action of the force? It is nothing but 1 sine 45. So accordingly, we obtain MO as 62.4. And please note here that this applied force of 60 lb, it produces a counterclockwise moment at the point O. Now finally, this is again a very simple structure wherein we know that the moment MO is the magnitude of the force is 7 into the lever arm. What's the lever arm in this case? That means from the point O, measure the distance normal to the line of action of the force. So it is 4 minus 1. So that is equal to 3. So 7 into 3, 21 kilonewton meter. So please remember that the unit of the moment, it should consider the unit of the force and the unit of the distance. Okay. Now here is another very simple example to demonstrate the computation of the resultant moment at a point O. So let me read the problem statement. Determine the resultant moment of the 4 forces acting on the rod about the point O. As you can see that the problem consists of a bent structure that is fixed to a wall at the point O, and the initial part of this rod is straight, having a total length of 4 meters, and the second part is inclined at 30 degrees to the x-axis and has got a total length of 3 meters. And please look into the x-axis that we have defined xy system, because it's essentially a 2D problem, and we can see that the origin of the xy system, it matches with the point O about which we need to calculate the moment. So, and here once again, while the example 1, it consists essentially only one force acting on a structure. In example 2, we find that there are altogether how many forces? 50 Newton, 60 Newton, 40 Newton, 20 Newton. So there are 4 forces acting on this bent rod. So we are asked to find out the resultant moment. Obviously, as per our earlier discussion, the resultant moment shall be the sum of the moments produced by the individual forces. So as usual, let us take the counterclockwise moments as positive, and accordingly we can find that the resultant moment at the point O is, let us go force by force, 50. What's the moment produced by 50 Newton about the point O? It is 50 into 2, and remember that it produces a clockwise moment, so accordingly it should be negative, so minus 50 into 2. And now regarding 60 Newton, as you can say that 60 Newton, okay, it passes through the point O, meaning that Okay, the lever arm or the moment arm for the 60 Newton will be 0. It does mean that the moment produced by the 60 Newton will be 0. So 60 into 0. So please make an important conclusion. When the line of action of a force, it passes through a point, the moment or the turning effect produced by this force about the point should be 0. Okay, and now let us consider the 20 Newton force. So it is 20 into, it obviously about the point O, 20 Newton produces a counterclockwise moment. So it's 20 into, what's the lever arm? As far as 20 Newton is concerned, it is nothing but, it is 3 into sine 30. Okay, so then finally we have got only one force, that is our 40 Newton. And obviously about the point O, 40 Newton produces a clockwise moment, hence it should be recorded as minus 40 into, what's the total lever arm or what's the total moment arm? It is this distance 4 plus of we have 3 cos 30. Finally, meaning that we have got a total resultant moment captured at the point O as minus 334 Newton meter. Now we can also make a conclusion here. The resultant moment is negative, indicating that the net moment acting at the point O will be a clockwise direction. Okay, so this is all our discussion regarding the computation of the moment of a force about a point using the scalar format. So in the next class, we will discuss how to evaluate the moment in a vectorial format, which will be useful for us for solving all 3D space problems. So let us end our today's class here. So we shall start with the next topic in the coming class. So thanks a lot for your patience.